Now let's say we consider example 3. In example 3 we consider the vector triple product, and this is a familiar relation that A cross B cross C, and we know about the result of this, that this is the Bay-Cave rule, means this is the B A dot C minus C A dot B. We know about this. Now let's say we start with this one. So this is the left hand side I am taking, A cross B cross C. Now let's say I take the ith component of this side. So this will be equal in terms of the epsilon ijk, is this is the ith component. So epsilon I, and then the first will get the j and the second will get the k component. And I know that this can further be expanded, epsilon ijk, and this is aj, while this one, this is the kth component, so I can write epsilon k, while the other indices will be different. Let's say they are L and M, and then B, L, C, M. So we are having now our relation equal to this. Let's write the epsilon terms earlier. This is epsilon ijk and epsilon k l m, and we are having aj, then aj bl and c m, and this I can write. Now this is KLM, I can write this Kij because it is cyclic, Kij, and then epsilon KLM and AJ BL CM. And now I know about this identity, that when two of the indices are the same, then I can write this in terms of the Kronecker delta, that this is delta, and the first index with the second index with the second index, delta IL and delta then JM, while the k index will be skipped, minus then I with M and J with L, and rest I will write the terms AJ BL CM, and now I can multiply the terms. So the terms are delta IL and delta JM, then AJ BL CM minus delta IM delta JL and AJ BL CM. Let's say I write it like this, delta IL and I write BL with this, and then delta JM and AJ and CM with this. JM, so JM I have split it, and this one I have split it like this. Similarly here I write delta IM and then CM, and I write delta JL and AJBL. Now I can write this one, let's say I write it this in bracket and then this one, similarly this one here and this one here. Now about this one, let me say that this I and L are the same. For let's say we do some supposition here and we say that I is equal to L or L equal to I, we can do both the things. So this is equal to delta I and this will be equal to BI, and then this one, this is one term. And what about this one? This one is the J and the M components. So the J and M components we write like this, that let's say the J is equal to M and J is equal to M. So we will write del J and AJ CJ minus, for I equals M, I write this delta II and CI, and this one for J equals L, I write this is delta J and J and AJ BJ. Now what about this one? Is we know that delta II is equal to 3 as in previous, but as we are considering only one component, so for one component this will be equal to 1, and I have BI, and then this one is AJ and CJ, because this is equal to 1, minus, then delta II is 1, so this is CI, and this is 1, so AJ and BJ. Now this is equal, as I am considering the ith component, this B is an I and C is an I. So if I write them as vector, then this is B vector. And if I look here to this one, this is the J component and this is the J component. It means that this is a dot product between A and C. So this is A dot C minus, this is a C vector, because this we are proving the ith component. So this is C vector and this is A dot B here. And this whole is actually the ith component of it. We have written this as a whole vector. So this is the ith component of it. And you see, we have actually proved the Bay-Cave rule here very easily with the help of Levi-Civita tensor. And that's why I told you that this is a very powerful technique, and with the help of this we can do calculate things very easily. Now let's say I do example 4, and example 4 is such that it is involving 4 vectors in a cross product. So I will not solve this one, but I will just convert this into the Levi-Civita tensor. So starting, let's say we are having A cross B, and it is in a cross product with C cross D. And now we want to find out this thing. So let's see, we are having the ith component of this A cross B and cross C cross D. So this is equal, if I take the ith component of this, so this is equal to epsilon ijk, and then the first one is A cross B, and this is the jth component, and then C cross D C cross D, and this is the kth component. Now I'm having epsilon ijk, and this is the jth component. So this is A cross B J, so I will write epsilon J here, and let's say I write LM with the next indices LM, so it is A, L and B M. And then for this one, this is epsilon K, and I write the other indices A's P and Q, so it is CP and DQ. And now I will solve this one. The three Levi-Civita tensors will be multiplied. So for this one, I will have to put some indices is the same, like this one. This is K ijk, this is JLM, so I can write this as Kij, and then from the cyclic order JKI, and this is JLM, so the Ki will be then summed with L and M and converted into Kronecker delta, and then later on I will treat this one. So this is the way to convert a cross product into a Levi-Civita tensor. Let me solve another example here, and this is example 5. This is one of the identity in the book, and we will solve this very easily with the help of Levi-Civita tensor. And let's say it involves a differential, and the differential is such that we are having del cross V cross W, two vectors and a differential of this one, and I know that what this relation is equal to. This is a very lengthy relation. I know that this relation is equal to W dot del in the direction of V plus del dot W in the direction of V. Now keep in mind one thing, that del dot W is not equal to W dot del. Although dot product is commutative, but these are not two vectors. This is actually a differential, and it does matter here that which one you write first. And then minus del dot V in the direction of W minus V dot del in the direction of W. This is equal to this. Now if we do the conventional way this thing, then it is almost close to impossible, that so many things we will have to solve. So if we do this thing with the help of the Levi-Civita tensor, then it will be equal. I take the ith component of it, del cross V cross W, and I take the ith component of this. So this is then equal to epsilon ijk, and then del J and W cross V cross W K component. And now I can write epsilon ijk and the del J, and this one I can write is epsilon K, and I write LM, the indices with this, and VL and WM. Now this one further I can utilize the relation. Just first convert this one. So this is equal epsilon ijk, and this is epsilon KLM, m and del j vl and wm. And we have written this thing in order. Let's keep this one in the bracket because this is a differential which will operate on this one. This we can take out as it's just a number. So this will be equal to, I can convert this one to kij, epsilon kij and epsilon klm. And what about this one? Differential will be applied on this. So this is the del j and then vl will be differentiated while wm will come with this, and then plus vl will come with this, and the m component, this is j, and wm, it will be in the differential. So this whole will be applied on this thing. And now I know that this thing is equal to delta and IL delta and Jm minus delta Im delta Im, this I with M and J with L. So JL, and this is the term which is here is del, no vector symbol here, del J and VL in the direction of WM plus VL and del J WM, and this is here. And now we apply this thing on this. So the two terms will convert, the two terms in product will be converted into four terms. I can write delta IL delta JM, and then this whole will be written as del J VL WM minus del IM del JL and then del J VL and WM, and then plus, this will be plus this term with this now. So del IL del JM and VL del J WM minus del IM del JL and this term which is VL del J and WM. So we have finally this result. Now is we have taken the ith component here, so I will take the ith component out of it, and this is with the v I can take this component. Now let's say we do here for removing this thing, let's say I is equal to L and J is equal to M. So I can write this one, that this is equal to, this will become delta I and it will be equal to 1 as it is one component and Gm, so it will also become equal to 1. And this one I can write in terms of, I will keep the I and the M here, so this will be delta M and Vi. Similarly, this is in the Wm, and I have written here the M I will retain while J I will just replace, minus here I will write I equals M here when I is equal to M and J is equal to L. So again I will write the I equal M, the J in M I will retain. So this is delta I, these are equal to 1, and now I will have minus del and I will keep the j here for L del j v L, so it will become Vj, and in the direction of W and I will keep this is, I will keep the M here because here I have kept the M, so I will keep the M here. Then plus here I will write I equals L and J equals M, and I will retain the I and the M components here. So this will be then equal, just keep the same I equals L, and I will write wherever there is L, I will replace it with I. So VI, and then del J and Wm. So Vi del J, and J I will have to replace with M. So this is M, and del J, and this is M, and it is in the direction, or means this is of M. So I have written this one, and then I will write the last term, and the last term here is I equals M and G equals L. So wherever I will have the terms, I will have to go accordingly here. So this is minus Vj, and del, it is G is kept, and it is in the direction, means del J, and M equals I, so I will write this is Wi. And now from this I can write that this is actually equal to del MVI. So from here I can write that this is, now this I can write is Wm del MVI minus, is this is the ith component, so I will keep the I the other side, and this is del dot V dot I, this is del J Vj, and here when we were writing Wm here for the second term, we have written I is equal to M. So is we will have to keep the ith component, so this one is equal to the ith component, and this will be the ith component, is we will retain the ith component, this we have the ith component, this we have the ith component, plus this is Vi and del M Wm minus Vj del J and Wi. So this I can now write very easily. This is W dot del in the direction of V minus del dot V, because the same component, in the direction of W, plus del dot M in the direction of V. So this is del dot W in the direction of V here, del dot W in the direction of V minus this one Vj, and this V dot del in the direction of W. So we have proved this relation. The del cross v cross this is equal to this. Here we will have to be careful in one thing, and that is very crucial, as I made one mistake here, that we will retain the ith component all over. So wherever there will be a replacement of the ith component, so we will just replace the L with I. This is the one thing we will have to take care, because we are taking the ith component. The rest will be just the replacement either in J or M, whatever they are, but that doesn't matter. But we will have to retain wherever an index is replaced with I, then we will have to retain the I component. And with this, our Levi-Civita tensor examples are done. And I hope when you will practice on this thing, then it is not that difficult.